The third and final step is to solve. We can use this set of conditions to solve for any of our unknown variables. So the third step, we want to actually solve our problem. If we look at this net force equation, we had come to a conclusion if we know Fx, that's equal to Tx, or vice versa, the magnitude. At the moment, we don't know either of those, so that's not super helpful for us. If we look at the net force in the y direction, we still have two unknowns in one equation. So again, not super helpful. So then I'd go ahead and move on to our second condition that we set up. And let's see if we can get some more solutions out of the net torque equation, or see if we can make any more progress toward a solution. So let's go ahead, since we know torque is RF sine theta, let's go ahead and write in those details for each of these forces. So the torque from Ty is that radius Ty sine that angle minus the torque from the bar's weight is that radius mg is the force sine theta, and then minus the torque from the sine's weight. I'll call this R2 because this is going to be a different distance. Big mg sine theta. All right, and all of this has to sum to 0. So R with no subscript, well, both of those were acting at the midpoint. Interesting thing, it didn't tell us the length of the bar, it just said it was length big L. And so the midpoint would be at L over 2. So we're going to have to leave that capital L in our equation for now and see what happens to it. So R here, L over 2, Ty we don't know, but the angle from Ty and R from the axis of rotation is 90 degrees. So sine 90 just turns into 1. We could go ahead and just drop that sine 90 at this step. And then we have minus R. Again, this was the weight of the bar at the midpoint, so L over 2 and mg. And this one was acting directly down, so another sine 90, so we can drop that part as well. And then at the very end of the bar, so the full length minus L will be that distance, and then mg. It's also acting perpendicular to the lever arm, so we can drop the sine 90. So this whole thing has to equal 0. And a good thing has happened here. We have L in every single term, so L will end up dividing out. We don't need to know the length of the whole bar. It doesn't impact the question. So I'm going to go ahead and divide that out. And I'm also going to go ahead and multiply everything by 2. That'll get rid of our fraction. So we'll be left with Ty minus mg minus 2 capital MG equals 0. So just a little algebra to kind of rewrite that expression. And what's so nice here, we know little m, we know big M, and of course g is our acceleration due to gravity. So now we can easily solve this for Ty. It's going to be the sum mg plus 2 mg, putting in those numbers, 8 times 9.8 plus 2 times 12 times 9.8, and we get the tension in the y direction is 314 newtons. All right, that's really helpful to us because now we are finally starting to piece together some of these unknowns. The question, however, did not ask for the tension in the y direction. It said, what's the tension through the wire? And so we really want to find T. But we know Ty, and so we can use a little trig to get there. I may redraw that really quickly. Oh, maybe I should try to trust it with drawing a triangle. Okay, good. So this was T, this was our 55-degree angle. This is Ty, of course, that's our 90 degrees. It definitely angled that a little bit, but oh, I don't know if we're gonna get better. I guess I'll try. Yeah, that'll work. All right, so we know this side, which is opposite to our 55 degrees, and we're trying to find the hypotenuse. So it looks like if we use sine theta will be Ty over T. If we're solving for T, we can multiply both sides by T and divide by sine theta. So T is Ty over sine theta. And putting in our values, Ty was 314, sine 55. And so then it's just a matter of putting that in the calculator, and we get the tension in the wire is 383 newtons. So now we have solved for the first thing it asked us for. I think I'll leave this one here, and then we'll find the force from the wall in the next video.